Hey guys, I hope you've had a chance to check out the HSC paper solutions, the 3 videos there that I posted for multiple choice and section 2, part A and part B. Let's have a go at the 2020 QATs trial. This was what was used at St. Philip's Cessnock for 2020 for the actual trial paper. All right, kicking right into multiple choice, we've got a nice derivative to start with. I'm going to split these two up separately. I'm going to say d on dx of x to the 4 plus e to the x. Well, x to the 4 becomes 4x cubed, and e to the x just stays exactly as it is because the derivative of the power there is just 1, so it's just 1 e to the x, which is b. Now, looking at some of these other answers, if you confused your exponential and log differentiation, you might have said a. If you just put those together and multiply them, you would have got c. If you thought this x jumps down the front here as well, then you would have gotten D. But hopefully not some runs on the board. First question there. Simplifying this fraction here, I'm going to factorize both parts. I have x plus 3, x plus 2 over x plus 3, x minus 3. Group those all together. My x plus 3's are going to cancel out, so it's x plus 2 over x minus 3. Just go looking for my right answer there, which is A. Again, almost like a year 10 or very start of the year 11 course algebra skill there to kick us off. Hopefully, again, runs on the board. All right, we've got to consider the amplitude of this, this sine function here. Well, we've got 3 different things that have been shifted here. We've got this half out the front. We've got this 3, which is going to impact our frequency. Our pi on 6 there that's been added on, that's going to impact our starting point. We have nothing that's impacted our midline, but that half at the front is what affects our amplitude. So our amplitude there is D, that's a half. Hopefully we were able to recognize what we're looking for there. No real trick or trap. You've just got to pick whether it's the half, the 3, or the pi on 6, and it's the half because that's this whole thing here is going to go, this whole section here is going to go between 1 and minus 1, have a range of 1 and minus 1, and that half at the front, well, that just halves our range, which means that tells us what our amplitude is, how high or low I go. Question 4 gives me a mean of 14 and a standard deviation of 2.1. Now I'm going to increase each of these scores by 4. What's going to happen here? Well, my mean tells me about my location. It's a measure of central tendency. My standard deviation tells me about spread. So if you'd imagine I've got my set of scores here, let's just say they were normally distributed. We don't need to know that or not here. If they're all sitting like that with my mean at 14, well, if I then go and shift them all and add 4 to each score, it actually just still looks like that. But now my mean is 18. And I've kind of made my imaginary scale there. But nothing's actually happened to the spread. It's the exact same curve that's just been shifted 4 units to the right. So my standard deviation will not change. So A is definitely wrong. B is going to be my answer here because the mean will increase by 4. Yes, it will. Every score goes up by 4. Then every score is 4 points higher, which means my mean is going to be 4 points higher. C, it's got them the wrong way around. That would be if we changed our spread of scores, if we left the middle ones the same, but then shifted the bigger ones further and smaller ones further away. And that would be C. D would be if we did something very strange here and we're going to have to multiply both the mean and the standard deviation by 4, which is not going on here. So B is our answer. All right, question 5 is a discrete probability distribution. I'm asked to find the expected value, the mean here. Well, my mean, I'm going to be able to say is going to be 1 times 0.23 plus 2 times 0.38 plus 3 times 0.21. 4 lots of 0.313, sorry, and 5 lots of 0.05. So what we are doing in each of those scenarios there is just going and multiplying score by probability that they occur. Think of fx, if you would, back when we were in year 9 and year 10, looking at a frequency distribution table. It's a little bit in the year 12 course as well. We're just going score times frequency and adding all those up to find what that arithmetic mean is. Now, if we add all those together, we're going to get C, which is 5. I'd imagine you get A if you go and add together all the probabilities. If you go add together all these guys, you would get 1, which you would expect because it's a probability density function. And you might get B if you forgot to multiply correctly. C is obviously correct, and I'm not sure exactly how you would get D. We've got a definite integral to evaluate here. I look at that and I go, oh, I've got a common factor of x. I could take that out. We could, but we really don't need to here. We just need to go and treat these two parts to my function separately. So that's going to be 3x to the 5 over 5, or I've added 1 to the power and divided by the new power, plus 2x squared over 2, which is just x squared, between 2 and 0. I don't need to write my full substitution here. I just need to get this answer correct. So it's going to be 3 times 2 to the 5 over 5 plus 2 squared. 2 to the 5 is 32, multiplied by 3 is 96. 96 over 5 plus 4, which is 20 over 5, which is 116 over 5. Answer B. Could just go do that in your calculator as well. There is the -0, of course, but because this is a multiple choice question, we're only looking for A, B, C, or D. No marks for working here. Straight out of the year 11 course here, we're given that sine x equals 5 over 13, and x is an acute angle, and we've got to find what cosine x is equal to. The poor man's way to go about this is to go find the value of x and then try to evaluate it by saying cosine of that angle. You can do that if you would like here because it is multiple choice and you'll probably be able to get away with it, but you won't be able to get lucky like that all the time. So the better way to do this is to go and draw a triangle. If I've got my angle x here, I could draw x bottom left, or I could draw it top right as well. It doesn't particularly matter. I've just chosen to do it bottom left. Now, my opposite is 5, because of course I've got opposite over hypotenuse here, going back to that very basic definition of trigonometric functions and ratios. Now, if I want to find this third side here, I'm going to go 13 squared minus 5 squared, which is 144. Square root that and I get 12. It's an exact value triangle as well. That's where all these 12s are coming from too in this. Now, if I want to go find what cosine is equal to, well, I'm going to say cosine x is equal to adjacent 12 over hypotenuse 13, and I get A. This is only true because it's acute. If it were an obtuse angle, or if it was in the third quadrant or fourth quadrant, we would have to take into account that it could be positive or negative. But because we're in the first quadrant here, all my answers are positive as well. We don't need to consider that. I've got 3 log expressions here. They're all to the base 3, and I want to evaluate log 3 of 100. Well, what we need to do in this case is to go and turn this 100 into 2s, 5s, and we could use 3s as well, because of course log 3 of 3 is equal to 1. We don't need to do that here because 100 doesn't have a prime factor of 3 in it anyway, so I'm just going to do 2s and 5s. So whichever way you want to break this down, log 3 of 100 is equal to log 3 of 10 squared. I'm going to bring that 2 out the front, which is 2 log 3 of 5 times 2, which is, again, I can split up and say it's 2 outside of log 3 of 5 plus log 3 of 2. And that's going to be equal to 2 lots of my expressions that I'm given here, 1.46 and 0.63. Which, as I add those two together, is going to be, without even using a calculator, I can see I've got 1.4 plus 0.6 is about 2 times 2 gives me about 4. So D is my answer. Key thing with a question like that is to always, if you're given these sort of arbitrary log 3, two different values, you've got to go turn this expression here into whatever you are given here and here. And you're always going to be able to do that as well. Remember, you've always got the log 3 of 3 up your sleeve as well. Whether it be 3 or whether it be some other base, you've still got that one up your sleeve as well. We've got a translation question here that appears in both year 11 and 12. I hope you're seeing that the year 11 questions do come up a fair bit in exams as they lead into year 12 ideas. We've got 3 things happening to our function here. Doesn't matter what type of function it is. It's got a vertical dilation of A units, followed by a horizontal translation of B units, and reflected in the x-axis. I'm actually going to eliminate 2 answers straight away using this last one here. If it's reflected in the x-axis, what we're going to need to do is turn it from some function that's up here into flipping that whole thing upside down. Well, how do we do that? We do that by multiplying everything by -1, which is either C or B, not A or D. So they're gone. Now we need to consider which of A or B is correct. So they both are reflected in the x-axis, but the other 2 parts are not correct for one of these 2. I undergo a vertical dilation of A units. Okay, well what that means is I'm going to multiply A by the whole function. So that's going to be out here. So we've already got our answer B, but let's confirm why it's correct. And a horizontal translation of B units to the right. So if I move in this direction, if I move to the right, remember that my critical points, or my turning points, if you'd like, well, even if we just think of a parabola, if I take my parabola and I shift its turning point 1 unit to the right, well, it becomes x minus 1 all squared, where it has shifted 1 unit right. So those horizontal translations occur by me using x minus something, which means that answer B here is correct. So B does all 3 of those things correctly. Question 10, we've got what appears to be a cubic function. We've got 2 turns at A and C, stationary points, and a point of inflection at B. So we want to know where is f dash x less than 0 and where is f double dash x greater than 0. So fx is less than 0 means I am decreasing, and f double dash x is greater than 0 means I'm concave up. Okay, so let's have a look here where those 2 things are happening. So I'm going to go with the concave up first. That's going to be blue. That's where I'm concave up. And where am I increasing? I'm going to be increasing where I could draw positive gradients. So, sorry, where am I decreasing where I could draw negative gradients? Well, over here, if I was to start drawing some tangents, they would be positive. That means I'm increasing there, not decreasing. So it means all of this is going to be my section where I am decreasing, where my first derivative is negative. So that means the domain I'm looking for is between B and C. It's written in interval notation here, which you'll notice that it doesn't have square brackets because I don't include B and C. B and C are where I have a point of inflection and my stationary point respectively. At those points respectively, the second and then first derivative are 0, not negative and positive respectively. So that's why we have those open brackets there. But that one wasn't really designed to trick you by giving one option that had the square brackets and one that had the round brackets. It was just whether you could determine what we were looking for here. We're looking for where these 2 things overlap, which is in that section right there. So the answer is C. Starting off in our written section, a couple of calculus questions to start. First of all, I've got a product rule. I'm going to say U is x squared, which means U dash is 2x, V is sine x, and V dash is cos x. So that means I can say y dash dy dx is going to be VU, crisscrossing them over, V being sine x times 2x, 2x sine x, plus x squared cos x. We can take out that common factor if you'd like. 2 sine x plus x cos x. But it doesn't really do anything. We're not asked to solve anything with it. It doesn't make it a much nicer or neater solution. So I'm actually fine for 2 marks right there. Biggest thing here is, can you see that it's a product rule? Can you do that product rule neatly and get some runs on the board nice and early? My second question here is an indefinite integral. You notice I've got no boundaries here, which means there's not going to be a substitution. First thing I think as well is plus c. I'll write that down over here so I don't forget. So when I integrate cosine, I get sine 4x. The way I approach these type of questions is, my first question is, okay, what did I start with? I started with cos, that becomes sine. They always switch between sine and cosine when I differentiate or integrate them. Now I need to think whether it's positive or negative. So if I was to differentiate sine, I would get positive cos. That's what I've got. So I'm okay here. Now, the other thing I need to do is divide by my derivative of my function part, which is 4x. So I'm going to divide by 4. And then, of course, my plus c that we acknowledged over here on the right that I needed to remember. I can get rid of that now. We don't need to write plus c all the way over there. And again, nice little 2-mark question just to get some runs on the board. No substitution needed. No real trick to that. Just basically, can you find the primitive of a trig function? We've got a first principles question here, which doesn't always get hit in exams, but it has here. Now, the first thing I would say is I can pretty quickly tell you that f dash x is going to be 2x plus 3. But there's no points for that here. Just writing down f dash x equals 2x plus 3 gets you 0 out of 3, I would have imagined. Certainly if I was marking this, I wouldn't be particularly looking for you to be able to find the derivative because it's so straightforward. What we need to do, though, is find an expression for f of x plus h, which means I replace x with x plus h in both locations here. I'm going to expand that out before I go put it into my limit statement. X squared plus 2xh plus h squared plus 3x plus 3h. And now I can go substitute in. So I've got f dash x is going to be equal to all of this here, which is x squared plus 2xh plus h squared plus 3x plus 3h minus x squared plus 3x. I'm going to put brackets around that to acknowledge that they both need to be taken away. Then I'm going to get rid of those brackets and actually call it minus x squared minus 3x all over h. And I also do need to include, I've forgotten to, this statement here where the limit where h is getting really close to 0. That's just how we write this expression. It's not the most user-friendly thing to do, but it's just one that's also not particularly hard as well. If you understand function notation and you can write a substitution and do a little bit of like terms and simplifying fractions, this is pretty straightforward. And really you should look at that and go, it's a bit of an annoying 3 marks perhaps. There's 3 marks that are pretty straightforward to get here. And you know the answer. So if you do make a mistake, you can hopefully pick it up somewhere and fix it. Simplifying all that using some like terms. Again, I need to include this statement. Limit as h gets really close to 0. My x squareds are gone, so are the 3x's. Anything that doesn't involve h is going to simplify. So I've got 2xh, h squared, 3h, all over h, which you'll notice they share a common factor of h, which I'm going to divide out. 2x plus h plus 3. Now I have no issue with allowing h to be 0. It doesn't actually become 0. I just had a problem with substituting it in here. I had a problem with letting it be 0 here because I'd end up with, well, that'd be gone, so would that, so would those. So it's just 0 over 0, which is undefined. But now I can just say, well, this component here essentially becomes pretty close to 0. It is approaching 0, which means that my first derivative, I don't need to write the limit anymore, is now equal to 2x plus 3. Hopefully we're able to get that. Again, runs on the board nice and early. Key thing with an advanced paper is that you get your first 20 to 30 written marks. You are cashing in on most of those. taking your time, not making silly mistakes, not coughing up marks there that are going to cost you later on in the paper. If you kind of approach it sort of like 3 lots of 30, and go first 30, I should be getting most of those. Next 30, things are getting a little bit more challenging, but if I'm a strong student, I definitely want to be still getting a fair number of those marks. And then your last 30, they're going to be hard. Okay, but if you cough up some marks and only get 10 of the last 30 marks right, but you got 25 and 20 in the first section, and then you get 7 for multiple choice, all of a sudden you've got a mark that's sort of in the 60s, which is a solid mark for a trial paper. If you're getting 15 out of 30 in the first 30 marks, you're going to struggle to get a strong mark because you're going to end up coughing up lots of marks later on as well, probably due to silly mistakes. We've got a stem and leaf plot here, and we've got to find the range and the median. Our range here is going to be 55 minus 30, which is 25. For our median, I'm going to count this up and say I've got 4 plus 5 is 9, 10, 11 scores. I'm going to halve that and say 1, 2, 3, 4, 5, 6. My 6th score is going to our median, so my median is going to be 44, which is the 6th score. I've got 5 below the 5 that I've crossed out. The 5 that I've left there, 7, 8, 9, 3, 5, are just the leaves that I've mentioned there. There's 5 above as well. I'm correct. Take the 2 easy marks. Don't make too much of a big deal of it. We've got an arithmetic progression here where we've got a shop assistant who's displaying cans of soup. Highly sought after item, I am sure. The top's going to have 3 cans, then the next row is going to have 2 more, then 2 more, then 2 more. So it means that my first term is 3 and my difference is 2. I'm going to write out Tn equals A plus n minus 1 lots of D, which is going to be 2n plus 1. So when n equals 10, it means I'm going to have T10 is 2 times 10, 20 plus 1, 21 cans in the 10th row. Might be easy to say, oh, why don't I just count them up? It would be easy to just count them up, but once I've got this expression for Tn, it's probably going to be useful when I see question 15 continues on the next page. Having that expression is probably going to help me for my next couple of marks. Now, as I said here, we had Tn equals 2n plus 1. And we now need to go and find how many rows this shop assistant can make if they've got 400 cans. So I've now got a sum of n number of terms is 400. We also know Sn is going to be n over 2, my first plus my last. Now the problem here exists where I don't know what my last is. I do know what my first is. My first was 3. Plus, well, I'm just going to write 2n plus 1 as my last term because that's my nth term in the series, whatever n happens to be, which is what we're trying to find. Now, all that's also going to be equal to 400. So now I've got the makings of a quadratic equation here. So I'm going to, first of all, multiply both sides by 2. So I'm going to have n outside of 2n plus 4 equals 800. Because I've doubled both sides, so 2n squared plus 4n minus 800 equals 0. I've subtracted 800 and expanded the brackets. If I actually look at it here, this over 2 at the start, I did have a common factor in there, and that was 2n plus 4. I could have just divided both of these things by 2. I'm going to do it now anyway. N squared plus 2n minus 400 equals 0. Just pause there for a second and try to find some factors. I can't find any factors, so I'm just going to use the quadratic formula. You'd be welcome here to complete the square as well. In fact, as I say that, it might be simpler to complete the square, so I'm going to say n squared plus 2n plus 1 is equal to 401. I've added 1 to both sides there. So that means n plus 1 all squared equals 401. So n plus 1 is equal to the root of 401. I'm not going to include the negative here. I don't need to do that because I know that there's not going to be a negative number in this pattern because n is positive. It's a number of cans in a shop. It's a positive quantity. So n equals minus 1 plus the root of 401. Finding my approximation for that, I get 19.02, which means I can make 19 full rows. And if we go back and check in our sum formula at the top here, which was sum of n number of rows. So if I go find the sum of 19 rows, I'm going to get 19 over 2 multiplied by 2 times 19 plus 4, which gives me 399. So I can make 19 rows using 399 cans, and I'll have 1 row left. We've got a question here about a double box and whisker plot here, acknowledging that my quartiles here, 0, 1, 2, 3, and 4, we call 0 and 4, of course, our minimum and maximum, and 2 we call our median, but they are 0, 1, 2, 3, and 4 quartiles there. They each represent 25% of the distribution between those, between their respective boundaries there. So what percentage of students in year 11 have a height below 160 centimeters? I'm going to go and say the top one is year 11. It's a nice 160 there, and that's 25%. Because these students here are all below 160 centimeters, and that's between the minimum and quartile 1. There are the same number of students above 175 in year 11, these people, as there are students above 175 centimeters in year 12, or these people. If there are 140 students in total in year 11, how many are there in year 12? Well, what that means is that year 11 is going to be bigger than year 12. So there's 140 students in year 11, and a quarter of them are bigger than 175. So I'm going to say a quarter of 140 is 35 students. So that means there's 35 students in year 11 who are taller than 175 centimeters. And there's the same number of students who are that height or above in year 12. So that means there's 35 students in this part of my box and whisker plot. Well, that means that's 50% is 35. So there's my total in year 12 is going to be 35 times 2, which is 70 students. Another way to think of it is to go, well, 2 quartiles in year 12 is the same as 1 quartile in year 11. So year 11's got to be twice the size of year 12. Or year 12's got half the size of year 11. Trapezoidal rule question here, where we are going to find the area of this garden bed. We're asked to use 2 applications. We can treat that as 4 separate shapes, in fact. 1, 2, 3, and 4. My height here is going to be 50 over 4, which is 12.5. If you're using the B minus A over 2n technique, that'll come out absolutely fine as well. Now I'm going to say my area here, I'm actually going to do this as one big formula, but it will be 2 applications still. I'm going to say 12.5 over 2. My first is 15, my last is 13 plus 2 times all the middles, which is going to be 25 over 4, 136 inside my brackets here, and when I go and multiply that by 25 over 4, I get 850 meters squared. I always like with the trapezoidal rule question to consider what would have happened if I just treated it like a rectangle. So if I just went and said, all right, it's a 15 by 50 rectangle, what would I have gotten there? I would have got 50 times 15, which is 750. it's in the ballpark. Clearly, what we've done here with the trapezoidal rule is much more accurate, but it gets me in the neighborhood to say, you know what, I'm probably right. I'm probably at least accurate. And if I've made a mistake, it's going to be a minor one, probably 2 out of 3 marks, not just a complete drop the ball and miss the question altogether. Fairly predictable trig question here. Nice one for us to get some marks up again here. We've got 3 towns A, B, and C. They're connected by high-speed optic fibers. We know that B is west of A, or AB run east-west, and town C is on a bearing of 210 degrees. So if I go and draw my compass plane here, I know that that's 210. So it means that this angle here is 30 degrees. 30 more than 180 gets me to 210. The other thing I can then discern is that that is 60 degrees. What gets me up to 270 degrees, which is on that east-west plane where B is west of A. So I want to find the size of angle BAC. Well, BAC is equal to, I can write 270 minus 210, which is 60 degrees. We can also do it the way that I've drawn it on there. You're not asked to show that it's 60 degrees, you're just asked to find what it is. However you get there, if you know that it's 60, you're good to go. And now we need to find the distance between B and C. That is going to be a cosine rule. So BC squared is going to be equal to 22 squared plus 30 squared minus 2, 22, 30, cosine 60, which is a half. So we're going to have 22 squared plus 30 squared minus 22 times 30, where these two, the 2 and the cos 60, which is a half, cancel each other out. You can just go straight to your calculator from this step here if you would like. And we're going to have BC squared is equal to 724, which means to go and find the length of BC, we need to take the square root of 724, which gives us approximately, as we're asked to do here to the nearest kilometre, 26.907, which is approximately 27 kilometres to the nearest whole number. It kind of looks like it fits in as well. I always like to check with this type of question. You say, oh, well, if I put a 27 there, would it make sense? Well, I've got an angle that takes up 1/3 of my 180 degrees, and it's the middle side between 22 and 30. It looks like it kind of fits in there and makes sense. We've got a function here, a graph that's defined by y equals x over e to the x, and we're asked to find the stationary points and determine their nature. To do that, we're going to need dy and dx. And this is a quotient rule where I've got u equals x, u dash is 1, and v is e to the x, v dash also e to the x. So dy and dx here is going to be equal to v times u dash minus u times v dash all over e to the x squared, which using our index laws is e to the 2x. So I'm going to have e to the x minus x e to the x over e to the, in fact, I'm going to leave it as e to the x squared, because what I can now do is take out my common factor of e to the x, 1 minus x over e to the x, e to the x squared, which becomes 1 minus x over e to the x. Now, what I need to do is find where this is equal to 0, because that's where I've got stationary points. Well, the only value where that happens is x equals 1, which occurs in the numerator. My denominator can't be 0 anyway, nor can e to the x equal 0 because it has an asymptote there. So either way, my only solution is going to be x equals 1. I need a y value to match that. Y equals, well, it's 1 over e to the 1, which is just 1 over e. Now, what I also need to do is determine the nature of this stationary point. Now, to do that, I could use the second derivative. I'm not going to do that here because that's going to involve quite another involved quotient rule. But what I can do here is I can go use a table, and so I'm going to say x is 0.9, 1, and 1.1, and find out what dy over dx is doing at those locations there. Well, we know that when x is 1, dy over dx is 0. When x is 1.1, I'm going to get 1 minus 1.1 over e to the 1.1. It's a positive number. That's the main thing to take away there. So this is actually going to give me a negative. Just going to call it a negative. I'm not going to worry too much about its actual value. And over here on the left, I'm going to have 1 minus 0.9 over e to the 0.9. Well, again, e 0.9 is positive. 1 minus 0.9 is a positive number. So that means that I've got a turning point that goes from positive increasing to stationary to negative decreasing, which means 1 on E is a maximum stationary point or turning point, because I've got that change from increasing to stationary to decreasing. If we'd done that with the second derivative, we would have also found that that was a concave down value in x equals 1, which would have given me the same thing. For 4 marks here, I'm asked to sketch this function, the graph of y equals x over e to the x, showing any stationary points. Well, we found that our stationary point was 1 on e, and that it was a maximum. Inflections, intercepts, and asymptotes. Okay, so I'm going to start there with the intercepts, and I'm going to say here that I'm going to have my y-intercept when x equals 0, x being 0, who is no issue whatsoever. So I'm going to have 0 over e to the 0, 0 over 1, that's 0. Okay, I've got an intercept there. Now, in terms of an x-intercept, well, that happens when y equals 0. Well, I've got one of those at the origin that I just found, but in my denominator there, I know that e to the x cannot equal 0. So that means my only intercept is going to be at the origin. So that means I'm done with my intercepts. Now my stationary point I've got ticked off as well. Let me go and mark that. That's 1 over 2.7. We can go calculate that approximately, but it's about this point 1 over 3, approximately there. That's going to be my maximum stationary point. Now, I've also got to think about any inflections. So we didn't find the second derivative in our first part of the question because we could do the nature of the stationary point without it. Here we do need it. Let's see what happens. Okay, so I had dy over dx is equal to 1 minus x over e to the x. So I'm going to need to do another quotient rule here. U is 1 minus x, u dash is minus 1, v is e to the x, v dash is e to the x. Crisscrossing those using my VOOV, I'm going to have d squared y over dx squared. My second derivative here is equal to v e to the x times minus 1 minus e to the x 1 minus x. And that's all over e to the x squared. We are likely going to be able to do that same simplification again. Let's see what happens. So I'm going to have minus e to the x minus e to the x plus x e to the x all over e to the 2x or e to the x all squared. Once again, we're going to get a similar phenomena here. I can put those together and make that minus 2 because they are just like terms. The e to the x's go, and I'm going to be left with x minus 2 on top. X minus 2 over e to the x, because I've simplified out that e to the x. So 1, 2, and 3 are going to go. Now, what I'm finding here is I've got a change in concavity at x equals 2. I can go and prove that. I'm not actually asked to prove it. But it wouldn't be a bad idea to go and check whether I go from concave up to down or down to up. It's likely that I go from down to up simply because what's happened in my first part of my question is that I've got a minimum turn here. So let's just go and check here. At x equals 2, I'm going to have y double dash equals 0. sorry, that's not x equals 0, that's x equals 2, sorry. At x equals 1.9, I would have y double dash is less than 0, and x equals 2.1, I would have y double dash 2.1 minus 2 being a small positive number greater than 0. That's right, okay? I've gone from concave down to point of inflection to concave up. Now I'm actually going to adjust my scale here on my graph to go and show this. I'm going to say this is my point now. 1 on E, where it's my my maximum turn, something like that. Now we've also got over here then 2 on E squared. So this is the point over here, 2 on E squared, by substituting in my value for x at my point of inflection, which is x equals 2, which is 2 over about 8. It's about a quarter. I've got this point here, which is my point of inflection, where I go from concave down to concave up. So something a little bit like that. It's not a turning point, it's a change in concavity. Now, the other thing to consider with this we're asked what the asymptote is, which, considering you're told find what the asymptote is, and we don't do a whole lot of work in advance with asymptotes, we do a little bit, it's telling me there's an asymptote. Now, the first thing to consider is, well, what would happen if I try to let something equal 0? Okay, so if I put x equals 0, and that's no problem because we already did that. I can't make the denominator equal 0, which could be a source of an asymptote. But the other place to check here, what's going to happen when x is really, really big? When it's positive, and really, really big when it's negative. So what's going to be happening over here, and what's going to be happening over here on my graph? So as I consider that, let's just go put in a big number. Let's pick 20. When I go substitute in x equals 20, my y value is going to be 20 over e to the 20. Well, 20 is a big number, but e to the 20 is an astronomically large number. So 20 over an astronomically large number is basically 0, which means that over here, I'm going to have an asymptote. Okay, so my curve is going to look something like this in this direction, where I have an asymptote being the x-axis over here. It's an asymptote. I'm going to get really close to it, but I'm never going to hit that because e to the x can never be 0. And what's going to happen is when x gets big, e to the x gets way bigger. And so I've got a big number over an astronomically large number, gives me basically 0. Now, considering what happens when x is really, really big and negative, let's do the same thing this time, but with negative 20. When x is negative 20, y becomes negative 20 over e to the negative 20. Well, that's e to the negative 20 being in the denominator. I could actually write that as negative 20 e to the 20. I've picked 20 as just an arbitrarily large number. You can pick 10, you could pick 72, you can pick whatever you'd like. Just don't pick 2 or 3. You need something big. Now, especially 20 is considered big here because my turn is at 1, my point of inflection is at 2, my intercept is at 0. Probably means that 20 is going to sort me out there. Minus 20 e to the 20, this is just a huge, large number. So that's not an asymptote. It just means my curve kind of looks like this. Okay, and that's what you'd be looking for. I'm going to label this point here 2 on e squared. Now this is, let me just caveat this by saying this is not an easy question. It's a little bit of a strange curve sketching question, but the skills are absolutely fair game to be assessed, and they were assessed in the 2020 trial from QATs. So you're finding those same things that you would normally be finding, your stationary points, your inflections, your intercepts, and your asymptotes. Your bog basic curve sketch doesn't have asymptotes, but this one does. And really, to test the asymptotes, you're saying, well, why can't my denominator be 0? Well, my denominator can't be 0 here because e to the x can't be 0 in the first place. That's removed from the table then. But also, what's happening when x gets really, really large in a positive and in a negative way to see where that asymptote is going to be. So this will be very clear. My asymptote occurs at y equals 0, when x approaches infinity, positive infinity. Okay, and that's y0 plus, which means it's just above 0. So if you take this point that we tested there, 20 over e to the 20, that's a really, really small positive number. And that's what that notation there means. And that happens when x approaches a really, really large number, which is positive infinity. Over here, the 0 is not an asymptote in that part of our graph. Okay, it's only an asymptote when x is getting really, really large. Linear regression question here, we've gone sublime to the ridiculous. 19 was very hard. 20 is something that could be common with a standard question. I would suggest doing part A here in your calculator by going stat a plus bx, and then entering your data, making sure that your points match up correctly. Then of course shift the number 1 key to get access to stats. You're looking for reg, and you're finding your value for A, which is your y-intercept, and B, which is your gradient. The giveaway here, if I just ballpark a straight line through these, which you're not asked to do, and go and do this, it's not even a straight line, but what I see is, oh, well, I've got a negative gradient and it's got a y-intercept somewhere in the 20s. Well, if I go take these steps here in my calculator, gives me about 3.4 hours. 3.38, we'll round that to 3.4 hours of exercise, which is fitting considering our equation was something like this. If I go to 15 there, I'm a little bit more than 3. And again, that is a very freehand drawing. It's a little bit more accurate than the previous one that I did. The other way you can do that is by using the X hat button in this regression mode. And that will allow you to predict. If you put in, I believe it's 15 times X hat there, it will take into account this data and will actually predict for you. But it might come out a little bit more accurately because we've rounded the 2.1 and the 22.1 for our gradient and y-intercept respectively. So you might get a slightly more accurate answer, but it really shouldn't take you too far away from that 3.4. Normal distribution question here. We've got 200 students in a year group. They have a mean of 162 and an SD of 4. What percentage of students are taller than 170? I always like the visual on this. Well, I've got 162. Our number we're looking for here is up here. It's 170, and that's going to be a Z score of +2. So what we're really being asked here first is what percentage of scores or students here are shorter than 170? Well, there's 50 that lie in here. Using our empirical rule, we've got 34% that lie in here and 13.5% that lie in there. That's by cutting up that 68 into half and then taking the difference between 95 and 68, cutting that in half. So what I've got is, my answer here is 100 minus 50 plus 34 plus 13.5, and that's as a percentage, which is going to be 2.5% of students. How many students, not what percentage, but how many students are between 158 and 170? Well, drawing a similar diagram there. This time we've got 162. We are looking at a -1 here of 158 and that +2. So we're asked really what area does that account for? What percentage does that account for? Well, once again, I know I've got 34 in there. another 34 in there, or you could have just said that was 68 in the first place, and a 13.5% there. So my percentage is going to be 68 plus 13.5, which is 81.5% of students. But we're told that there's 200 in the year group, so that means I would essentially double that percentage to get 163 between my two scores, which are 158 and 170. Could add centimeters to both of those. All right, we've got a trig function here to solve. There's normally sort of one of these per advanced exam. This one has got a little trick to it, a couple of them, given that it's 3 theta, and it's between 0 and pi, not 2 pi. But let's see how those two things play out here. Standard thing I want to do here is I want to rearrange so that I've got my ratio as the subject. Now what I'm going to do here, I'm actually going to let 3 theta equal A, and now I'm going to say therefore sine of A is equal to negative a half. What I want to look for now is what my solutions for A are going to be. Well, I've actually got a little issue here, because if I want to solve this between 0 and pi, I've actually got no solutions, because this is what sine of A looks like between 0 and pi. It's only positive. What I need to acknowledge, though, I'm actually going to solve this between 0 and 3 pi, where A lies between 3 pi and 0, because A is 3 times larger in terms of my domain. So I'm something like this. Okay, so I need to go find these two solutions down here. They're going to be in the equivalent of what will be the third and fourth quadrant, without getting to that second revolution, which would be over here. Now, my acute angle here would be pi over 6, so my acute would be pi over 6. Now, in the third quadrant, that's pi plus pi over 6, which is 7 pi over 6, and 2 pi minus pi over 6, which is 11 pi over 6. Now that's my my two solutions there. But what I do need to do here is acknowledge that that means that 3 theta is equal to those things, 7 pi and 6, and 11 pi and 6, and divide them by 3. So theta is going to be 7 pi and 18, and 11 pi and 18. A quick little sketch here could really be helpful for this type of question. Don't worry about the 2 and the -1 there. If you're just sketching sine 3 theta, if you try to do it with the 2 and the -1, it'll become very complicated, or at least more complicated than it needs to be. If you just do it with the 3 theta, you just take your normal sine theta, but acknowledge that it happens 3 times faster, and go, all right, well, my normal wave would be 1, 2, 3. Oh, but that would be in 2 pi, so I'd actually just get rid of, these bits, kind of as I have over there on the right, and just acknowledge that it's 1.5 waves, because I'm only going between 0 and pi. The fact that it's between 0 and pi, not between 0 and 2 pi, actually means that I've got less solutions. If I made that between 0 and 2 pi, I'd actually end up with 6 solutions, and the question would be harder. But it's made a little bit easier. It is a harder question, but it's made a little bit easier by the fact that it's only between 0 and pi. We've got an exponential growth question here. First of all, we're asked to find the initial population. I'm going to do that by saying when t equals 0, my p is equal to 1,000, e to the naught, e to the naught being 1, so that means p naught, or my initial population, is equal to 1,000 ants. We're also then told that when t equals 5, where of course t in this question is in weeks, my p is equal to 15,000. Well, it's tripled. So we're asked to show that the value of k is 0.5416. Now I'm going to substitute in 15,000 equals 1,000 e to the 5k. We're trying to find k here, not t. I'm going to divide by 1,000. So we're going to have e to the 5k is equal to 15. My population is 15 times larger. I think I said it was 3 times larger. That's not true. It's 15 times larger after these 5 weeks. I'm going to take the log of both sides. I'll rewrite that in logarithmic form, and I'll have 5k equals the natural log of 15, or k equals the natural log of 15 over 5. Putting that in our calculator, we do find that we get that number as required, 0.5416 to 4 decimal places. Part C here, we're asked when will the population first exceed 50,000. I don't like solving these like an inequality. You can do this. 1,000 e to the kt is greater than 50,000. I actually just like to find where it's equal to 50,000. Now, obviously, that's not going to be a whole number, but it's going to give me a number that I can approximate with and consider my answer at the end, rather than getting mucked around by this inequality. It's not too bad here because I've only got positive numbers, but sometimes you can get caught up with the negative numbers and do I change the sign? If I just solve it like an equation, you'll see what happens. So I'm going to divide by 1,000. I've got e to the kt equals 50. Population's 50 times larger. I've left it as k as well, even though I know what k is. Take the log of both sides and I get kt equals log of 50. So t is going to be equal to the log of 50 over k, which now I'll bring this in here. My actual value for that, I'd encourage you not to use 0.5416, even though you could use it because it was in the previous part of the question. Doing that and putting it in my calculator, I find that I get 7.223 weeks. Well, what that means is after 7 weeks, I'm not quite at 50,000, and at 8 weeks, I am well over 50,000. So what that means is it occurs in the 8th week. And the question reads that way too. During which week? It doesn't ask you what the time is. It acknowledges that in the question that it's not a whole number, but does ask you to find in which week does that occur. It occurs in the 8th week because we round that up. Even though we would naturally round 7.2 down because it's not over 7.5, we round this up because we say, well, at 7, it's not going to be there yet. We have to round up to get at least 50,000, or it exceeds it in the 8th week.